Hey everyone, my name is Fraser Cain. I'm the publisher of Universe Today, and this is your weekly space hangout for Friday, September 18th, 2015. And we've got another awesome special show for you guys today. So I'm going to go through our regulars first, and then we'll get on to who our special guest is. We're also going to be talking about exoplanets. We're going to be talking about Jeff Bezos' rocket company, icy moon with a global ocean, more images from Pluto, what's happening with the Orion crewed mission, and the upcoming eclipse and observe the moon night. So joining us this week, we've got Morgan Rehnberg. Hey, Morgan.
Hey, Fraser.
We've got my Astronomy Cast co-host, Dr. Pamela Gay. Hey, Pamela.
Hello.
Welcome back to the new season of the Weekly Space Hangout, featuring Fraser's painted downstairs living room, which you always give me a hard time about. And we've got Paul Sutter joining us again. Before, he was our special guest. Now, he's going to be a regular. Hey, Paul.
Yay!
Yay! And you're in Europe right now.
Yeah, I'm in Trieste, Italy. It's right behind me, over there. The city.
Trieste is
you
over
can kind
there.
of see it.
Yeah.
Yeah,
Awesome.
It's over there.
All right, great. And we've got a special guest this week. We've got Professor Sara Seager from MIT. Hi, Sarah. You're muted still. But great. So as always, we're going to take about 30 minutes, and we're going to sort of take some time and interview our special guest, and then we'll move on to the sort of the stories. I will ask a bunch of questions, but everybody feel free to jump in and ask your questions. And especially, I want to say to all of the live viewers who are watching us right now that you can also give us some of your questions. So I'm going to say hello to Jim Meeker, Matt Woods, Leonard Lindstrom, David Dunn, Nancy Graziano, Richard Clark, Guido Bibra, Tony Lynch, Bert Wolters, Giselle Sabarin, Yolette Avron, Ignatiy Romanov-Cherengovsky, and Joe Richley. You got to tell me how I'm saying this. Joe Reichel, Patrick Festa, yeah, and that's everyone so far. So, hey everybody, if you're watching this right now and you want to ask a question to the panelists or to Professor Seager, you can just go wherever you're watching this, just click that you want to interact with the we're interacting with the audience. Click that. You'll see the video, but then you can then go ahead and see all the chat that's going on and go ahead and ask one of your questions. So that would be great. All right, so Sarah, why don't you give people a bit of a background on who you are and what you do?
Sure. Well, I work at MIT, and my main focus of research is exoplanets. Actually, I work on two separate things. One is atmospheres of exoplanets. We make models using physics and chemistry and big computer codes and try to understand what we're seeing when we have data from Hubble Space Telescope and other telescopes in exoplanet atmospheres. So far, we have a few dozen of them that have been studied to varying level of detail. My other job is in the role of helping with space missions to be launched in the future so we can find more planets. And the one that's going on here right now is called TESS, the girl's name TESS, Transiting Exoplanet Survey Satellite. And TESS is going to be following in the pioneering Kepler Space Telescope. And TESS is going to be an all-sky survey. It's going to look at all the bright stars all around the sky, looking for small, rocky, transiting planets. And my job is, what I'm planning for my job to be in the future, and a lot of other people are planning this too, is we're going to take that pool of planets and look at the very best ones with the James Webb Space Telescope. And we're going to look at their atmospheres, just like we've been doing now for the giant planets with Hubble. And we're going to look for signs of that a planet might be like Earth, and that a planet might have water on its surface, or that it might even have signs of life in the atmosphere.
So can you put the search for extrasolar planets kind of in context for us? I mean, we're all familiar with say the Kepler mission, which unfortunately sort of had its breakdown. TESS is sort of in that same line, right? It's a transiting, it's a satellite searching for transits, but in this case, smaller bodies, right?
Right. Well, essentially, the funny thing is that now it's actually, believe it or not, nearly impossible to put things in context because there's so many planets. We know of thousands of exoplanets, and every star we think has at least one planet. And so there's so many missions. Anyone you ask probably has a different favorite one that will happen sometime now or in the future. And so right now, transiting planets are just all the rage. And that's because we can find the smallest planets with the transit method compared to any of the other 5 or 6 planet finding techniques.
Right.
So it's not just TESS, but there's even other missions still that are going to go up and do the same kind of thing.
And so then you mentioned that we've already got a chance to see the atmospheres of some of these other planets. And we actually talk about this quite a bit, especially Pamela and I on Astronomy Cast. Why is it so important for us to be able to analyze the atmospheres of these extrasolar planets?
Well, there's one simple reason, actually, and we can liken it to our greenhouse atmosphere here on Earth. That is, like, without the atmosphere, a planet would have a very, like, the atmosphere basically controls everything that's happening at the surface of the planet. And when, you hear in the news, hopefully you talk about this, when you hear of a planet that's Earth-like, we actually have no idea if it's Earth-like yet. We just know it's Earth size and how much energy from the sun is hitting the top of the atmosphere. Actually, it's the composition of the atmosphere and the mass of the atmosphere that will ultimately control the surface temperature. So we're sort of doing everything we can to, prepare for that day when we have atmospheres of the small planets. It just provides a lot of information. It's not perfect by any means, but it's a window into the planet.
And so then what will the future hold for this? One of our greatest sadnesses in Astronomy Cast is the cancellation of the Terrestrial Planet Finder, which is, of course, this mission that was, proposed a few years back and eventually was canceled, but it would be able to actually analyze the atmospheres of Earth-sized planets orbiting other stars. And, of course, the goal, as you said, right, is that we would be able to see if those worlds are actually Earth-like by the composition of their atmosphere. So I know that the Terrestrial Planet Finder was canceled, but where do we sort of stand in that search for potentially other Earths and really to be able to study their atmospheres?
Well, right now, the Terrestrial Planet Finder, you're right, it had been canceled. We have a kind of rebirth, actually, of direct imaging. You have probably talked about the Gemini Planet Imager and the other instrument spheres like that in Europe, in Chile, rather. And so we have a kind of direct imaging that's being reborn now. And actually, I just finished 2-year slog of working on a imaging concept called the Starshade. And in parallel with the Starshade, another team worked on, originally these were called reduced scale TPF studies, but no one likes to hear that you reduce like your favorite thing from the past. So they got called probe class studies. And actually it was amazing because it wasn't just a paper pushing activity. We had a real team of engineers at JPL who worked really hard in solving the right problems. And we did, bring the Starshade in particular just to a level of visibility, and I hesitate to use the word maturity, but much more mature. And so that kind of is still ongoing. There's nothing planned yet that will find small planets. So while we're waiting for the Starshade and other things to become reality, we're relying on transiting planets and looking at the atmospheres as backlit by the star. And that's what we're hoping to do with small rocky planets. They won't be Earths, they'll be small planets transiting small stars. So I think of it like not like Earth twin, but Earth cousin.
Yeah, and so this idea of the Starshade, right? This is a coronagraph. This is a
Hold on 1 second, because I actually have something that I can show everybody.
Oh, really? This is the best. Oh, wow.
This is a 1% scale version of the Starshade, 1% scale. So the Starshade is a 30-meter in diameter screen, and it will block out the starlight so that only the planet light will enter the telescope. And this Starshade will have its own spacecraft, and it will be flying like very, very far from the telescope. I'm even afraid to tell you how far. But the Starshade is a very special shape to block out the light directly. So it's like the coronagraph is the version of the Starshade inside the telescope. This would be fully outside of the telescope.
So can you explain the shape then? Because it does have a fairly unusual shape to it.
Yeah, these little tips here can draw blood on this.
But that shape, how will that be put in front of the stars to be able to sort of piece out the planets?
Well, first of all, just address the shape. If you put a big circular screen in space, it wouldn't work actually. You would have diffracted light from the star around the edges, like dropping a pebble in a pond, there'll be ripples. You'll have these light ripples from the star. And that really is bad because the first ripple would be 100,000 times brighter than the planet that you're looking for. And so that very special shape actually, what it does is it uses diffracted light to your advantage. The waves still interact, the light waves, but it's like, this analogy is like not the right one, but it helps understand it. If you were to drop a pebble in the pond, and instead of getting ripples, the pond is perfectly smooth. and all the ripples are pushed out to the edges. So that shape allows the light to work with itself in a way that suppresses the starlight in the middle of the image, and the outside of the image is where all the light gets put. So how would it line up? Well, I could give you a very detailed answer to whatever detail you want. So I'm not sure what level of detail you're looking for here.
Well, we have a very technical audience, and as you see, there's a lot of doctorates even on this panel. But I think if I understand correctly, a thing like this star shade could be used by observatories that are already up there. Hubble, some of those other instruments could already use a star shade like this to then begin doing some of this analysis. Especially James Webb, right?
Right. Okay. So it's a yes and a no for those. It's a yes because in general, sure, we think every telescope should go up there and be star shade ready. It's a no because of a couple of things. One is the telescope has to be away from Earth's gravity. Earth's gravity is bad for formation flying. Your question was a good one because the formation flying is one of the three hardest things about the star shade, and there's still a ways to go in developing the sensing that we're going to have to need to do the formation flying. So Hubble wouldn't work for that reason. The James Webb would have been a great one. It's not perfect for this example. It doesn't right now have anything on it to communicate with the star shade. You literally have to put a telescope on the star shade just to see the James Webb Space Telescope itself. It's not really that bright. It's like an 18th magnitude star or something. It's pretty faint. That's one problem with using the James Webb. The other problem with the James Webb is the bigger the telescope, the bigger the star shade has to be. And the size of the star shade we would have needed for the James Webb, it's just a little too big for comfort compared to what we're building upon, which are large radio deployables that have already been launched to space. Finally, the James Webb, if you've looked at the great movies of it and stuff, it's all open, right? It has this 5-layer sun shield, and then it's just so open. And there's only certain ways the James Webb can point relative to the sun. And so when you put the star shade in that kind of thing also, you have a very limited part of the sky where you could do, for the types of stars, numbers of stars you could search, just because of the configuration of having to formation fly, but always have the sun in a certain location. So,
right.
Plus actually, the James Webb had its own problems, as I'm sure you've already talked about. So we weren't allowed to think of adding anything to it.
Right.
Now, with sunshades like this, do you actually have to scale them or re-engineer them based on the wavelength so that a sunshade that might work in one window of the infrared wouldn't work in another window?
Yes, actually, it does have to be scaled, but it does better than all the other starlight suppression techniques in just how wide of a wavelength it can cover. So typically we're not thinking of the infrared, we're thinking of visible wavelengths, and you could design the star shade that worked across all visible wavelength bands.
Yeah, you said you didn't want to sort of terrify us with the distance, but it's on the order of thousands of kilometers, right? They're really far away from each other.
Tens of thousands of kilometers.
Yeah. Yeah, I remember doing some articles about this. Must have been maybe 10 years ago. I'm trying to think, was it Cash Webster? I'm trying to remember someone who was originally was proposing some of these right. concepts. Yeah.
The star shade is sort of an interesting concept because it had been thought of since the 1960s by Spitzer himself, and he had written about it in context of the Hubble Space Telescope. And every decade it was revisited by someone, usually someone really good with optical physics. And there was never any way to really think of building it until recently, actually. Webb Cash brought it back to life. He figured it out independently, but it had been there sort of all along in some form. And only really in the last few years has it started to receive a lot of attention as being even feasible. And for formation flying, we do try to make it sound a little better because we're like, well, we dock at the space station under Earth's high gravity. Maybe you've talked about Grail that went to the moon, and it did laser ranging. So we've had different versions of formation flying. None of them have been as precise in one regard as the star shade, and that really has to just do with sensing. But we do have, the team does have a plan of exactly how this would work, how we would find it, how we would acquire it, how we would line up.
Yeah, and there's, the LISA mission, which would be searching for gravitational waves, is taking that formation flying to a whole other level of precision. So definitely that precision flying work is important for many missions. So then, so we were all sad, and we literally almost every episode we complain with Astronomy Cast about how the Terrestrial Planet Finder was canceled. So you're giving us new hope that in fact, thanks to these techniques, this capability will be brought down to more inexpensive missions and sort of support satellites, and that maybe then that's something that's more digestible by the people who write the checks. But isn't this the most fundamental question that almost human beings can ask? Are we alone in the universe? And this, this instrument, this methodology could get us very close to an answer. So, why wouldn't we want to build a million of these?
Here's the thing. Well, funnily enough, we used to have this phrase, all roads lead to TPF. So we have one of our people here is in Italy, all roads lead to Rome. We'd say, like, no matter how you do exoplanets, eventually you're going to have to go to space and do direct imaging. We had Kepler was phenomenal. We have direct imaging on the ground. We have microlensing. We have radial velocity. We have so many ways to find planets. But ultimately, you're going to want to go up and do direct imaging. And I think it's just the complexity is just daunting. If you think about it, we're limited by the wavelength of light where stars are bright, and hence planets are bright and reflected light. And we're limited by the laws of physics. And that, when you work through all of this, it puts you right up at the limit of what we're actually able to engineer, maybe ever. For the internal coronagraph, the overall telescope, I'm skipping a lot of math here, it ends up having to be stable literally to like tens of picometers. The wavefront has to be stable to tens of picometers. An atom is tens of picometers. We're sort of right up at the limit of what we're even allowed to do with physics and engineering, what the universe is going to let us do. So I think one of the reasons it's so obvious, like, why don't we just do it now, is it's very complicated and very costly. And all of that gets us like the nearest 100 stars, and what comes next? How do you do the next thing if the thing right up front is very busy, is very, very challenging.
Yeah. So, based on the kinds of planets that have been turned up so far, what are some of the ones that have really surprised you and, were very unexpected? I know sort of, the concept of hot Jupiter sort of blew everybody's mind when those were discovered. So what are some other examples of planets that maybe, you weren't expecting to see?
Well, I think the biggest example, and I could probably speak for a lot of people, are the so-called, we call them sub-Neptunes. They're the planets that are 2 to 3 times the size of Earth. Neptune is 4 times the size. Earth, of course, is 1. Like, who knew, that our galaxy, at least where Kepler was looking, has so many of those. Like, the most common planet we know of that we can measure about is not existing in our own planetary system at all. And I think that is one of the most astonishing examples from exoplanets, in all of planetary science even.
What would one of those look like if we did have one in the solar system and we could send a Voyager 3 to it? What would it look like?
Believe it or not, we actually don't know. We can enumerate all the possibilities for you. It's as if I gave you a box and I said, here's this box. It could have 3 different things in it: water, iron, and rock. Now, can you tell me what proportions those 3 different things are in the box? I'm sure some of the viewers can think through this, because the answer is no, you can't actually, because you could have only water and iron. Water's very light, iron's very dense. Or you could have only rock, and you could probably come up with a combination. There's no unique answer actually. So these planets just fall in this bizarre region of density where they could be one of a number of things. And, I always think like nature is smarter than we are. So probably anything we can think of is there. So in some ways I could tell you what we think the possibilities are, but we really don't know. So that's why they're so exciting, because we just don't know what they are. And they fell into this region of, we call it parameter space, where we can't actually say for sure.
Right, and so like literally until you land a probe on the surface of one of these worlds and start measuring the earthquakes, or will you actually be able to really get a sense of what's going on inside of it? But I guess direct imaging would sure help.
It would help. We think that looking at their atmospheres could actually give us a big clue as to whether they're rocks with hydrogen helium, like a miniature version of Neptune, or Jupiter rather, or are they rocks with a thin, water planets, like a scaled up version of one of Jupiter's icy moons that has a thick steam atmosphere. So atmosphere observations could certainly help. And indeed, we have observed atmospheres of transiting ones of these, but we've seen nothing. We've only seen like a flat spectrum, and so we think they're cloudy, but we don't know. So yeah, you're exactly right. The atmosphere can provide more information. It might not solve all the problems, but it should be able to narrow things down.
Right, and so if you saw like volcanic outgassing, things like that, you could get a sense of if it has volcanism, rock, metal, whatever. That's pretty amazing. So then, based on what you've learned so far, you're saying like we don't have any of these mini Neptunes here in the solar system. So what does an average solar system in the Milky Way kind of look like? If we're outside of the norm, what is the norm?
I mean, it may be one of those cases where there really is no norm. I'm gonna have that a question. Actually, I just have to admit I can't answer it off the top of my head. I think there's probably, there's a really good paper that is sort of on my list to read. It's a review, an annual review in astronomy and astrophysics of planetary architectures, and I'm sure it addresses just this. But likely, either we know already, or at the end of the day, there's no one norm, but there may be like 10 common types of planetary systems out there. I think at the end of the day, that's sort of how we'll look at things. Like you may have talked before about the so-called compact multiple object systems, where they have 5 planets interior to where Venus would be. And there's, Kepler found a lot of those because those are easy to find.
Right, and there may be some situation, like we talked about the hot Jupiters, and sort of we've talked about in the past the mystery of how these Jupiter-sized worlds could migrate potentially through the solar system, and what kind of implications that would have on the other objects in the system. And so you might have places where everything got thrown out, and places where those never formed, and so they were a little more stable, and places with Oort clouds that are much bigger than ours. It's crazy, all the different combinations, and every time it's sort of like a new one. So, obviously, I think you would love to find, Earth 2.0. Do you think that data exists in the Kepler data, or do you think we're gonna need to wait for tests to be able to dig this up?
I think we're going to need to wait for. Let me think for a second. Well, I don't think TESS will find Earth 2.0. It'll find an Earth-like. It might find an Earth-like planet, but not because it can't find an Earth around a sun. It wouldn't actually be Earth 2.0. I don't think we can find it in the Kepler data, because remember, Kepler just gives us the size of the planet and the orbit. We have no other information.
Well, when I say Earth 2.0, I sort of mean, an Earth-sized world, roughly the mass of Earth, orbiting a sun-like star within that star's habitable zone. And so, a lot of the stars that have been, we found all of those classifications, but they're orbiting a red dwarf star. But so it's that,
I prefer to call Earth 2.0 more like Earth itself, because what people forget is that Venus and Earth, to any planet finding technique we have now, including Kepler, they look the same, actually. We wouldn't know if one was, like Venus and one was like Earth. So, but can Kepler find something smaller? There might be. People are trying as hard as possible to see if there is an Earth-sized planet in an Earth-like orbit that's the right size. So I think that work will go. We won't know for a couple of years probably.
Yeah, and I know the problem with Kepler was that it broke down just to the point where it was going to start to gather that third year's worth of data and be able to actually start putting that together in a, like it lost all that further information. It had to kind of start from scratch with its new observations. So. So we've got a couple of questions here that have started to pile up, and I thought I would throw some from the viewers. I just want to remind you, if you're watching this, we would love to hear some of your questions for Professor Seager. So Elad Avram wants to know, I'm finding it hard to understand how, at such great distances, you can still differentiate the star and the planet well enough to block one and not the other. So could you elaborate on this?
Okay, let's see.
How can you see the difference between the star and the planet? And I guess this is the point, right? It's incredibly difficult to do this, and hence the star shade.
Right. Well, I think I've just got to think about this for a moment. It's true that those stars are very, very far away. We're still talking about the closest ones, but we do work it out into a number, like a fraction of a degree. What fraction of degree angular resolution on the sky do we have to make it? And we do have a number, and you can work this out for yourself. Just say 1 astronomical unit, at 1 parsec, you can kind of work out what 1 arc second is. And so we're actually looking at something tiny, like 100 milliarc seconds, fraction of an arc second. But the math actually does work out, and you could do something simple. And if you didn't know about the laws of diffraction, forget about that for a moment, because it's very complicated math. Just sketch it out for yourself. A circle at some distance from telescope, and the angle to where the planet and star is, and you can get your head around it maybe a little better that way by working that out.
Yeah.
So it's a small angle, but it's not insanely small.
And this is the type of thing that we're starting to be able to think in these fractions of an arc second as we look at, for instance, the data coming back from Gaia, which is doing amazing positional measurements, and we have experience dealing with this kind of precision with various different techniques. This is just a new technique to approach this level of precision.
Yeah, just amazing. I mean, you sort of see the same thing as well with some of the ground-based observatories with the high degrees of interferometry with all of these different observatories all working together as one. So this seems to definitely be a theme that's coming back again and again, which is getting the instruments sort of perfectly tuned to be able to do greater and greater science as
Yeah, I feel like
usual.
a lot of branches of science, people just want to do better, smaller, more precise. So yeah, it's a natural evolution of the field.
Yeah, absolutely. This question comes from Thomas Treiniker. What kinds of rogue planets, if any, have we discovered?
That's
Have
a big,
any rogue planets turned up?
well, there's two different categories of rogue planets. One are the ones that are kicked out of a planetary system, and people think that like there's at least one of those per every star. That planetary systems are formed full and things are ejected all around. We haven't found any of those yet. There's been reports by microlensing where they've seen signals of planets that might actually be rogue planets, but we're not sure if they're just so far from the star that they're truly unbound objects just floating around randomly, or if they're really just if they are bound to just a star that's quite far away, like 1,000 AU. That's one type. Another type people like to argue over are just big planets, like 10 Jupiter masses, young objects people see. And that goes on the question is, what's the smallest object that can form out of a collapsing cloud? And we don't totally really know that, but people do argue about these objects. There have been ones found. We don't know their mass. We don't know if they're really like failed brown dwarfs or failed brown dwarfs or planets. We're not sure which category they're in, and people argue about those also. But those ones weren't kicked out of any planetary system. They would have just been born on their own.
Right, and I guess like brown dwarfs, it's just sort of how cool you can detect objects like this down into the infrared.
Partly that is how cool you can detect, but then you have to assign a mass to it because all you do is measure brightness. We're not really sure what that object is in nature. Did it have some fusion going on the inside, in which case it's not a planet? It never fuse anything. We can't. So the answer is we don't know if rogue planets have been found. People have found good examples of planets that might be, but the community hasn't agreed on them.
And to return real fast to the separation, an object that is 3.26 light years away, which is 1 parsec, the separation between a star and a planet, 1 astronomical unit, the Earth's distance away from that star, that's 1 arcsecond on the sky. And our best ground-based telescopes have better than 1 arcsecond per pixel seeing. And so this starts to be, if you can just block out the smear of light from that star, you can start to get at the faintness of that planet.
All right, so I got a couple more questions here. Now they're coming in fast and furious. So Matt Woods has asked a question, and I'm not sure I completely understand it, so maybe you'll understand it. You guys are speaking some kind of code with each other. Would you be able to guesstimate what the color of the atmosphere is with all the data that you'll get from TESS? So would you be able to use TESS to tell you the color of a planet's atmosphere?
With TESS, we will not. TESS is like Kepler in that it only has 1 wavelength band. It goes from about 400 nanometers to 800 nanometers, because the more photons, the better. We don't want any moving parts. We don't want filter wheels, so there's no color information with TESS. We'll use follow-up telescopes to try to get some color information.
But that would be theoretically possible with some of these further on observations. You could see that planet is kind of blue like Neptune, while that one is blue like Earth. Blue and white like Earth.
You know, I was just about to say yes, of course. We will use the James Webb, but the James Webb goes to 0.7 microns or 0.6 microns. So we may not really be able to assign planets a color in the sense that he's asking.
It'll happen with the future telescope that you are working on, and we will help get pushed through Congress. So awesome. Fantastic. So this question comes from Ignatiy Romanov-Chernigovsky. So if the light shield is not attached to the telescope, then will it work as a standalone spacecraft or operated through a telescope, or will it just be an inert object with the telescope moving to the correct position? So how will the sort of the star shield, the light shield, work?
The star shade would definitely have its own spacecraft, and in some cases that we think of, it would have lots of fuel, and every time. We forgot to mention this, but the questioner understands this. The star shade has to move across the sky for a new target star. So the Starshade's a fully functioning spacecraft. It would have communication ability with Earth itself and directly with the other telescope, because when they formation fly, they're just talking to each other. In other examples, we imagine that the Starshade is not just an inert object in space, but the telescope is the thing that moves around the sky, and the Starshade stays mostly where it is, but it will have to alter itself a little.
Right. I guess that's really the big issue is, as you said, because the Starshade has to move to be in between the telescope and the target star. Oh, this is great. We've got a picture here from Pamela. It's going to have to move quite a bit if you're going to want to look at different objects. I'm guessing, you'll try to look for a lot of things that are all in sort of the same area, but it's going to be moving around a lot, and so it's going to need a ton of fuel.
Exactly. And we spent so long. We had a person working nearly full time for over a year to figure out an optimal path across the sky, going from star to star for stars of interest.
I mean, could you do something like the stereo mission and have it go on, say, an Earth leading or Earth following orbit, and then over the course of the year you would get sort of a different view of the sky as you came around? Or
let's see. Well, the spacecraft and telescope would both have to be,
Yeah, both be Earth following, maybe to one of the Lagrange points, right? And then just...
Yeah, that could work. I don't know if it would necessarily be beneficial, because the problem with those is as they start drifting away from Earth, you'll lose contact eventually. We've studied those ones. The Earth is really big initially, and it's bad. It's contaminating the image, but eventually you drift away far enough so that you can look away from it.
Right. Well, if you do use that idea, you can have it. Okay, so this question comes from Jeff Morris, who's one of our fans, but unfortunately he's got to work. But he's passed along a question for us, which is, can you say what is your favorite type of theoretical exotic planet type? So what is a theoretical type of planet that people are thinking of that maybe will turn up eventually?
Well, I think our favorite type of planet is the so-called water world. One of these mini Neptunes may be one of them, that it's like a scaled-up version of one of Jupiter's icy moons. Imagine for a moment a planet, we're just calling it loosely 50% or more by mass water. And it would be really amazing to imagine a planet like that. Inside would be ice, like high-pressure ice, really solid, but not the type of ice we have in like our ice cubes. We could imagine some of these would have like a thick steam atmosphere overlaying not a liquid ocean, but perhaps an ocean that's supercritical water. So we love exotic things, and water is an interesting substance. So that would be my favorite exotic planet to find.
So even if a planet like this was in the habitable zone, you would get layers of ice further down as the gravity and pressure and temperature heats up?
Exactly. There's a lot of phases of high pressure ice. A lot of people have heard of Ice 9 because it was in that Kurt Vonnegut novel.
Yeah, right.
But that's not it, because that's on the surface, and remember that was supposed to freeze all the water on Earth's surface. But yeah, there's definitely a bunch of different phases of ice at high pressure. And it's just because everything's squeezed together, it can't be liquid.
That is fantastic. Ronnie Pearson asks, could you detect an Exo Oort Cloud with this technique?
That's a good question, actually. It's a great question. Let me think for a second. Not sure, actually. Possibly.
I know. So, Elad Avron says, "Don't skimp on reaction wheels," and so that is the ongoing joke around these parts, which is we figure most missions would have been successful if they just installed more reaction wheels, and some of our fans have actually gone on to design spacecraft with dozens, hundreds of reaction wheels.
Really?
So. Yeah.
By the way, there's one point I just want to mention about Kepler, just in case you guys didn't know, that it wouldn't have just taken 1 more year. It actually would have taken 3.5 more years. Because in addition to this mechanical failure, there's an astrophysical surprise. I'm sure some of you have heard of this, but what happened was that Kepler was designed for our sun, assuming that all stars are quiet like our sun is. We think they were based on everything we could measure. But it actually took Kepler to measure the precise variability of sun-like stars. And it just turned out that stars were more variable. Sun-like stars are a little bit more variable than our sun. Our sun is in like the 1/3 quietest spin. There's a tiny, tiny bit more variable. And people initially, before the reaction wheels failed, people on the team were like, it's so funny. Our sun is not a sun-like star. Because our sun is not like the average in variability. That little extra variability, it was white noise. But it meant that Kepler would need to look twice as long. Instead of having a 3.5-year mission to find the Earth-sized planet, it would actually need a 7-year mission. So it was a little bit of a tougher thing. It was two things that were bad. One is nature threw us this little tiny surprise, and the reaction wheels failed. So that's what happened. So that's the reason we don't get to the Earth. Kepler was supposed to find 50 Earth-sized planets and didn't.
Yeah, so that sounds like 10 reaction wheels, 10 spare reaction wheels, maybe 12. Cool. So I think we're a little more than halfway through the episode, so why don't we switch to talking about some of the news that's happened this week, and I know you're a fan of all things space as well, so you're going to stick around and join us and talk about some of these things, so that would be awesome. But thank you so much for sort of sharing the current state of exoplanet research. It is probably half of what we talk about on the show, so we're all really excited for what's going to come next. Awesome. Okay, cool. So let's talk about a new. Well, not. Jeff Bezos' space company. Paul.
Yeah, I mean, it's not new, but it seems to be coming into the news a little bit more. I think Elon Musk and SpaceX have hogged all of the space company news in the past couple of years. But all along in the background, Bezos has had this Blue Origin company, and they've been somewhat secretive and tight-lipped, not spilling a lot of beans about what's going on. But they've done a test launch of their rocket and everything. And Bezos last week made this big announcement that he's playing the game too, the billionaire leading us to Mars. So I think it's going to be, in about 10 years, I think there'll be a shorter list of billionaires who don't have space companies. And it seems, which is great. It's like all these rich people that grew up on all these sci-fi stories and the traditions that we all share now want to make those dreams come true.
Well, a few have thrown in the towel. I know that John Carmack shut down his Amarillo Aerospace. Not that he's a billionaire, but it's an expensive game to be in. Although I was reading a report that, and this is just about to turn into This Week in Musk, that SpaceX has booked more revenue than the total value of Uber, I think. Anyway, billions and billions and billions of dollars. They've got hundreds or dozens of contracts already signed and set. And so when you think about just how hilarious everybody thought SpaceX and Blue Origin were 10 years ago, and now they're all just giving them their money, maybe it's time for him to have some competition. Like it's kind of scary now that it's almost going to turn into a monopolist. So.
Right. I think Bezos. I think he said in the next 2 years, or no, he said by the end of this decade, he'll be running supply missions on his rockets and his capsules. He's in cahoots with United Launch Alliance, I think. So they're like a real rocket company that have been doing this for a long time. So it's not like it's just like Bezos in his basement of his mansion, designing rockets. There's some serious brain power and some serious political clout and economic clout coming from the partners on this Blue Origin project. So I agree. I don't think it's going to end up being monopolistic. There will be some competition in space, which is that's an awesome phrase to say.
Yeah, exactly. So, Sarah, I guess a related question for you, I'm sure, is, a lot of these kinds of planet hunting, space-based planet hunting missions really rely on the launch cost of the rocket. So has this sort of the reduction of launch costs started to bring some missions that used to be just wild imagination start into kind of the realms of reality for you guys?
Well, one thing you'll be interested to hear is the TESS spacecraft is going to launch on a Falcon 9. And the cool thing is, if you think about it, I don't have a picture to show you right now, but there's the fairing, and TESS is like that big in the fairing. So wow, I mean, it's still cheaper to get the Falcon 9 and put the little tiny TESS there. It's like the size of 2 washing machines stacked on top of each other in the Falcon 9. So we're already starting to do that. In the case of TESS, our cost didn't include launch. NASA's covering that as part of the program. So that was their choice to go there. But yes, definitely, we're relying on, we're hoping that all these launch costs will definitely keep going down so that we can launch our missions.
Yeah, I mean, it's like the two going hand in hand. There's the miniaturization of the actual instruments, and you can't really miniaturize glass, big lenses, but the actual instruments, the electronics, the cameras, the CCDs, all that kind of stuff comes down in size.
Passes down in size because we're looking at very bright stars, so we didn't need to have a big telescope. But the launch cost is key. Definitely.
Yeah, and launch costs coming down, miniaturization coming down, just means more missions going up.
So that's an interesting question. How many CubeSats can fit on a Falcon 9?
I'm sure someone's done the math.
It's probably so many that it'll clutter up our low Earth orbit. So.
Well, there is interesting work being done where a lot of different folks are looking to share rides to space. If you talk to the Google Lunar X Prize teams, many of them are looking to basically share a launch vehicle and then race across the lunar surface. With these successful Falcon 9s and that big fairing, it's getting possible to split a ride and commute together.
So maybe SpaceX really is an Uber competitor.
Yeah, exactly. All right, let's move on. Morgan, we've got more images of Pluto.
When are they going to stop? It was just a week
18
ago.
18 months. There's 18 months of data.
Just a week ago that we were sitting here oohing and eyeing at last week's new amazing Pluto images. And let's see if I can screen share what we have to wow us this week. So we've all seen this picture now 1,000 times, where we have one of these mosaics from New Horizons showing the full disk of Pluto, and you can see this now famous heart-shaped region.
It really looks like Pluto the dog to me now in this picture. Like you see his little ear, you see his nose, his head, not a heart.
And if we zoom in on any region of this, we can really see that there's kind of a lot of almost three-dimensional structure going on. And this kind of grabbed our attentions right away. And the pictures released this week really show that in detail. So now if we really drill down into one of these regions, we see pictures like this. So this is a picture taken by New Horizons after it passed sort of by Pluto, and now the sun is sort of behind Pluto, and we're looking back with New Horizons towards the sun. And this is a really useful angle to take when looking to image very diffuse things. And one of the things that's very diffuse at Pluto, of course, is its atmosphere. And so what we can actually see in this image is the Pluto atmosphere, and we can even zoom in further here and kind of see it stretching up above the surface.
Look at that picture. I apologize to all the people who are listening to the podcast version of this episode, but this is just one of the most. I think this is the best picture that's come back from New Horizons so far.
It's astonishing.
Yeah.
And
we're looking at the atmosphere. We're looking at these mountains made of ice. We're looking at these glaciers of potentially methane and ammonia ices moving around. This is unbelievable.
The Pluto atmosphere is fascinating because over the course of a Pluto year, and of course we actually haven't even observed an entire Pluto year, but what we have seen is that the atmosphere seems to kind of thicken and then decrease over time as it gets closer and farther from the sun. And so what New Horizons is going to allow us to do is compare observations that we've made from the Earth using techniques like stellar occultations to actual observations made right sort of at the object. And it'll help us reconcile, as we were hearing about last week, reconcile the observations as they actually exist near the Pluto surface from what we can see long away. But of course, that's just up here. The rest of this image is almost equally amazing, and it shows in just astonishing detail the mountains that we're seeing at the edge of the heart. So on the right side of this image, you can see the smooth area that makes up one of the corners of that heart region. But then we can see all of this very chaotic and twisted terrain. And this, I would venture to say, looks nothing like what we were expecting. The idea that we had for Pluto was one informed by Triton, Voyager 2 observations of Triton, which is the largest of Neptune's moons, and it showed a very, very strange, complicated surface, but it didn't have nearly the detail to show what we can see here. And there's another image that they returned that is going to show us even closer detail on what we're looking at here, and just how structures like this form and how long they persist is something that we don't have a good answer for, or even what they're made of. Because we know most of Pluto is made up of water ice, although its surface is covered in at least a thin layer of nitrogen ice, with some other gases also forming ices onto the surface. But as we talked about last week, a lot of these ices probably aren't strong enough to sustain mountains of these heights. And we're talking about mountains that are kilometers high here. So on the same order, the same scale as what you would see here on planet Earth. And to see them rendered so sharply in an image like this, I think really drives home what dramatically varied terrain even a very small portion of Pluto can have.
What's really cool about this is no one quite knows what to make of it. And Emily Lakdawala was able to get what I think is the best summary quote. The quote comes from the Curiosity rover project scientist Ashwin Vesavada, who said, "Holy moly, that's one of the best solar system pictures ever! Hysterical laughter. Wow!" He didn't say hysterical laughter, he just hysterically laughed, which I won't do into my microphone.
Think of a picture just more immediately grabbing than this.
Yep.
It just has the beautiful backlighting, the atmosphere, the terrain, the fact that, holy crap, this is Pluto. It's just exceptional.
And there was a new dump of LORRI data today, and they're slowly but surely starting to add some search and sort features to the websites. We're still looking at 9 to 12 months before the actual image raw data, not bin, not scaled, not compressed data, hits the planetary data service, or system rather, and that delay before we get the full-scale images is just to give the poor scientists who aren't really sleeping chance to, well, the spacecraft has been a couple decades in the works, and they are allowed a whole 12 months to publish their results.
So let's move on to the upcoming eclipse and International Observe the Moon, Pamela.
So they don't actually occur in that order. So tomorrow is both Talk Like a Pirate Day and International Observe the Moon night. So I encourage you to tell everyone in the voice of a pirate to go out and look at the moon and find the event near you. This is a strange confluence of events that we are quite happily silly about. International Observe the Moon Night is a celebration that's been around since 2010. It came out of the Lunar Reconnaissance Orbiter team, and it's our chance to remind everyone that we're still learning about the moon. There's a whole lot of people that are like, hey, I've been alive since Apollo, and hey, I've been alive since after Apollo. And they think that we haven't learned anything new about this nearest world in all those 40-some-odd years, but the truth is we have amazing instrumentation currently orbiting, currently taking data that is at better than half a pixel per better than half a meter per pixel resolution, which means that if we were to all assume the snow angel position on the surface of the moon, we'd appear as small, strange-shaped specks in those high-resolution images. So tomorrow, go out, look up, find an event near you. There are hundreds and hundreds of events scheduled on every continent of the planet except for Antarctica. And just remember, we are still out there discovering our own solar system. In addition to that, the moon is going to put on an amazing display for us later this month. Tomorrow we're going to have a smaller crescent, but as we head towards September 27, 28, we're going to have an eclipse that will be visible in its entirety for the Mississippi eastward in the northern United States, for all of the Maritimes in Canada. Mexico, we're sorry, you only get half of it. But South America, you will see all of it, as will Western Africa and Western Europe. This will be, for many of us, an early evening eclipse, which means that you can go out with your kids, look up, and with all the volcanic activity that's been going on around the world, our own atmosphere will probably give us a nice bloody red moon, which can be really interesting to explain how the interplay between the sunlight and the atmosphere affects the color that we see the moon, and we can learn about our own atmosphere by looking at the moon.
Yeah, and you potentially gonna try and live stream it, maybe?
I'm going to try. Still need to finish organizing that.
All right.
Too many grants coming up.
Well, maybe we'll do like a special mini virtual star party and just hang out and talk about space while we watch the eclipse. Especially,
that's kind of the goal.
Yeah, because I know I'm gonna have cloudy skies because it's Canada.
Hey,
on the West Coast.
I have a question.
Yeah.
What is a pirate's favorite kind of eclipse?
Partial eclipse.
A part that you get a point. Thank you. I just thought I didn't have to embarrass myself to answer that. Sorry, it took me 5 minutes to come up with that joke.
That's brilliant. That's absolutely brilliant. I may ruthlessly steal that tomorrow.
Yeah.
At CosmoQuest, we're actually encouraging any of you who have cloudy skies and can't see the moon in real life to go online and help us map out the moon in this amazing high-resolution data. So that's cosmoquest.org/moon. And for those of you who are in the St. Louis area or feel like being in the St. Louis area, we will be doing a real-world event at Annie's Custard here in Edwardsville, Illinois. So come take a look through the telescope, but please don't get your custard on it.
All right, I think we've got time for like one more quick story. Let's talk about a new icy moon getting a global ocean. Paul.
Yay, everyone gets a global ocean. It's like an episode of Oprah. She's just, you get an ocean, you get an ocean. So Enceladus, the moon of Saturn, for a long time we've known that probably has a ocean like in the southern pole region. That's where there's all these water ice plumes coming out that kind of feed the E-ring of Saturn. But some new observations from Cassini were looking at the wobble of Enceladus as it goes in its orbit around Saturn. And you throw this wobble at a computer, just like the process Sarah was describing. You have a black box that has certain properties. You're trying to guess what's on the inside. And apparently the models support, or the best guess, to explain the particular wobbles of Enceladus have that the icy crust on the surface is actually disconnected from the rocky core of the moon. And the only way to do that is to have a liquid water ocean, almost like grease in like two ball bearings or in a joint or something. And so there's probably a global ocean. It's not just constricted to the southern polar cap. It surrounds the moon. And so it's just another moon in our solar system gets a globe-spanning ocean.
Yeah, this has to do with the moment of inertia, just to throw out fancy science words. And the same physics that allows you to figure out if your hard-boiled egg is hard-boiled or not when you spin it on the counter. It's the exact same physics that they use to figure out, is this a hard planet or is it filled with liquid like that egg you forgot to boil?
This is great timing for this as well, because this effect, which is called libration, we can observe in our own moon. The moon doesn't have an ocean underneath it, but it does wobble back and forth in its orbit as it goes around the Earth. And so we can actually see more of the moon from Earth than we should be able to, just because of this effect of libration. And if you were patient and you went out and took a picture of the moon every night, what you would see is it would wiggle back and forth just a little bit. And so we've actually known that this effect can exist now for thousands of years.
Fantastic. Okay, well, I think we're just reaching the end of the hour now, so why don't we wrap things up? So where, Morgan, do we find out more about Morgan Rehnberg?
Well, you can always follow me on Twitter, at Morgan Rehnberg. This week I was tweeting about the presidential debate. We'll see if I can sustain that for the next 15 months. Otherwise, you can see what I've been working on most recently over at morganrenberg.com.
Fantastic. Any planetarium shows coming up?
So we just had a great one last Friday, and we're working on a new one for a month from now. Just going to examine how we've used the night sky over the last few thousand years as a very practical tool for things like figuring out when it's going to rain and when we should plant our crops and how the seasons change.
Awesome. Pamela, where do people find out more?
I think we have everything summed up over on cosmoquest.org. Click on the community tab, and under Join Us, it lists all the podcasts, all of the vodcasts, well, like this Hangout on Air, and read our blog and find out about all the science we're doing. And then, of course, I happen to live at Starstrider on Twitter.
Fantastic. All right, Paul, this is new for you.
Yeah,
Where
you
do people find out more?
Yeah, you can follow me at Paul Matt Sutter. That's PaulMatTSU, 2 more T's, and then an ER. That's on Facebook and Twitter. I post to both of those pretty regularly. But then you can also go to pmsutter.com, which is short for Paul Matt Sutter. That has all my research activities, and there's a whole page with all the shows and podcasts and YouTube series, live appearances. Like everything I do is on my homepage at pmsutter.com.
And what's your podcast again?
Ask a Spaceman.
Ask a Spaceman, and people
And you can, askaspaceman.com.
And then you sign up to it?
You do what the title suggests, and that is to ask a spaceman. And then I pick questions that people ask to answer on the show, and I devote like a half hour to an hour to each question. Coming up next month, I just recorded an episode about what banged the Big Bang. Was a question I got, and so I'll be talking about the very early universe in my next episode.
Fantastic. All right, and Professor Seager, where can people find out more about you and what you're working on?
I would just say Google. Just Google me, and you'll find some stuff. I don't really have a very active presence on a variety of things. Sometimes I post on Facebook, but that will do.
Just look at the big list of planets that have been discovered, and they'll see your actions. Great. Well, of course, you can see me on Twitter, fcain, on Google+, etc. Subscribe to this if you haven't already on YouTube, and that way you'll get updates when we do new shows. I want to also mention that the folks from the Weekly Space Hangout crew, which is, of course, the community that works together with this show, they're really our producers now. We have 500 producers, which is the WSH crew. They've created a Twitter handle, which is WSH crew, so you can follow that. And of course, there's the community on Google+, the WSH crew there. And it is they who lined up the guests. They lined up the Pluto Palooza last week, and they reached out to Professor Seager this week, and they have scheduled the upcoming guests. So I couldn't ask for a better partnership in a group of space fans who are really driving their own destiny. So if you're interested in the show, you want to participate in the community, join the WSH crew community on Google+, and you can help sort of suggest guests and help figure out what's going to be in the show. Cool. Well, thanks everybody for joining us this week. Really appreciate it. Thanks for all the questions, and thanks to the panelists, and of course, Sarah, thank you so much for joining us. It's awesome. This is so exciting.
You're welcome.
Okay, great. Well, we'll see you all next week.
See ya.
Thank you.